Haqq-Misra, like
Haqq-Misra.
Huckleberry.
Okay, perfect. All right, let's get started. Hi, everyone. I'm Fraser Cain. I'm the publisher of Universe Today. I've been a space and astronomy news journalist for over 20 years. We report all the news on Universe Today, but I like to bring you behind the scenes so you can see the kinds of interviews that we do with the experts in the field. And today, I'm joined by Dr. Jacob Haqq-Misra from... Actually, what is the place? Where are you from?
I'm at the Blue Marble Space
Right.
Institute of Science.
That's right, yeah. And so who are you? What do you do?
I'm a research scientist. I'm an astrobiologist. I'm interested in finding, life on other planets. But for my day job, I use computer climate models, the kind that you might use for weather prediction or climate prediction on Earth. And we use these to study the habitability of other planets. So that could be Earth through time. That could be, planets like Mars or Venus, and that could be exoplanets around other stars.
Is that related? Because I remember about a year ago, maybe there was a really interesting set of papers that came out where they were simulating weather conditions on Earth, but also Venus in the past, as well as maybe some fairly familiar exoplanets like Proxima Centauri B and so on. That kind of work?
That's right, exactly like that. I
Yeah.
mean, we think the physics of atmospheres should be, operate on planets generally, and so, understanding climate on Earth helps us understand climate on other planets, and then looking at some of these weird planets helps us maybe understand the physics of Earth's climate a little better.
So when you think about the planets that we've discovered so far, do you think that we're getting a sense of how habitable these might be?
We are starting to. I think what we're getting a sense of is there's definitely a lot of planets, probably at least one per star, if not more, and rocky planets like Earth in this habitable zone where you could expect liquid water to occur. That seems to probably be really common. That said, we're just getting to that threshold. It's easier to see bigger planets than smaller planets. So the first generation of planets that were discovered were large Jupiter-like planets, and so we're kind of getting closer to that Earth-sized planet. And there's some planets that I think are you can claim are relatively comparable to an Earth size. But that sweet spot of an Earth-like planet around a sun-like star in the habitable
Yeah.
zone. I think the best targets are still to come. We're still just getting to the point of demonstrating that planets are everywhere and that we can find them.
I mean, we think about the planets in the TRAPPIST-1 system, they're probably we know they're very close to their red dwarf star. They are probably receiving radiation, larger flares than the kinds of things that the sun can put out. They're probably tidally locked to their star. What implications do you think that would have on the habitability of a planet?
Yeah, those are great questions. That's one of the things that keeps me funded. It's great. But yeah, what you said is exactly right. We expect, these planets to probably be, tidally locked. So one side of the planet is in perpetual daylight, one side is perpetual night. There's this zone of perpetual twilight on the edge called the Terminator region, which is kind of fun to think about. Maybe that's where life would exist. It kind of depends too. Which there's TRAPPIST, D, E, and F. The planets are all named by the letters. Very unoriginal,
Yeah.
unimaginative. But the planet E might be the best one to think about for maybe being Earth-like. That doesn't mean it's Earth-like, but at least in terms of being that right distance where we could try to think about what sort of habitable atmosphere it might be. But the other planets, planet D, which is in a little closer, it might not be like Venus. There could be ways that it might be more habitable. And planet F might be an ice ball, but maybe not. I mean, we don't have the data yet to say if they have atmospheres and what they are. So right now you have the masses of the planets and the orbital distance, and how much starlight is falling on them. So you can kind of play some guessing games using your climate models to say, okay, what are some plausible atmospheres given what we know about it? And then that can be useful because you're at least preparing for future observations. And if something could never be observed on that planet, not to look for it. But really, the exciting moment will come when you get some spectra, you get some, observe the atmospheres of these planets to figure out what molecules are in there, what's its atmosphere made of, and then that'll help give us some real data for these models.
I mean, I think those observations from James Webb are the ones that I'm most looking forward to. Like, of course, I'm looking forward to all the cosmology stuff, but to see that spectra from James Webb of the atmospheres of the TRAPPIST-1 planets, if it's able to produce that, is going to be really exciting.
Oh, I'm excited about that for sure.
Yeah, yeah. Now, you came across sort of my desk because you were the lead author on a paper discussing, I guess, what existing telescopes and missions have the potential to find technosignatures out there in the Milky Way. So, can you talk about the process? Because it wasn't just a paper, right? It was a conference, and this is the end result of a discussion.
That's right. It was about 2 years ago. It was at the beginning of COVID, and me and my colleagues had talked about doing a workshop about technosignatures to try to get people in a room together and talk about where to go, how can we make some serious progress on finding directions for technosignature science. And then the pandemic happened, and we decided well, let's just move forward with this anyway. People are still excited, at least at that time, 2 years ago in August, we're excited about online events. And it was a nice small event, which worked out. It was about 50 people. We met on Zoom for a week. I think about 4 hours a day for a week. And the first 3 days were presentations by just some of the, big names and then, students studying technosignatures. And then the last couple of days we spent having, discussions and being in breakout groups to try to figure out, this paper that you mentioned was talking about current and future missions, things that we built or are building or are designing, and what the potential would be for advancing technosignature science. One of the other papers was, kind of like our wish list, like, okay, if we weren't really constrained by budgets or any, you have to be constrained by what's realistic and what we can do. But so, yeah, if the funding were not an objection, what are the kinds of things we would really want to do? And so that was the second paper that came out of this workshop.
All right, well, let's tackle these one at a time then, because both are really interesting to me. So how did you classify the kinds of technosignatures that you're going to be searching for, and then compare those to the capabilities of the missions and telescopes that exist right now?
Right. Well, we focused on technosignatures in exoplanetary systems. And so what that rules out is technosignatures in the solar system. I'm not saying there are no technosignatures in the solar system. In fact, I'm very interested in that. That would just be a separate paper, mainly because there's so many solar system missions. The way that you would talk about that is just different. So we just focus on exoplanetary systems. And in our paper, we focus on non-radio. Again, not because I don't think radio is important, because radio has been studied a lot. And so and NASA was interested in funding exploration of other aspects of technosignature science beyond radio. So we mentioned radio for sure. Maybe this is the classic approach to SETI, the search for extraterrestrial intelligence. You point a radio telescope at a system. Maybe there's leakage, their TV transmitters and radar, you pick up on that, or maybe there's a beacon and they're trying to communicate with us like that. So that's fine. But we actually focus more on what would you see in an exoplanet system, either things in the atmosphere or things around the planet, or maybe something that we're not even doing. We're putting pollutants in our atmosphere now, so you can think about searching for that. We're putting satellites around our planet now. So you could imagine having a lot more satellites and that being detectable. But you could think about other future extrapolations, like building megastructures, something like a Dyson sphere or something else that we can conceive of doing, but we're not going to do anytime soon. But we could at least think about what detectable signatures, things like that, like megastructures, astroengineering might look like.
So, you gave a few examples, but I know that people in this field have been brainstorming for quite a while, and there's a lot of really clever ideas for the kinds of signals that a advanced civilization could either intentionally or unintentionally give out. You gave some examples, but I would love to hear sort of a more deeper list of some of the ideas that you think are pretty clever.
Absolutely. Yeah, well, so I'll start with pollution. And so when you talk about pollution, the idea is there anything in a planet's atmosphere that shouldn't be there? Is to put it in a simple way, We do this with biosignatures too. If we want to look for life on a planet, not necessarily technology, but life, you look for gases in the atmosphere that probably wouldn't be there if life weren't there. And one of the ideas is oxygen and methane are both produced by life and they destroy each other. So the fact that we have them both on Earth is due to life. Chlorofluorocarbons are one example of a gas in our atmosphere. These have been banned by the Montreal Protocol and been replaced with safer alternatives because they help deplete ozone, and the Antarctic ozone hole was a big political issue. And the Montreal Protocol actually was one of the few, examples of an environmental success through policy by banning this dangerous chemical. But they have long lifetimes. So even some of the potent greenhouse gas CFCs that were emitted back, in the 80s and such, they're still lingering in our atmosphere.
Right.
So if you were to point a telescope at an exoplanet, or if aliens were to point a telescope at us and observe our planet's atmosphere in the infrared part of the spectrum, you might notice some extra absorption from these CFCs. There's no known biological process to make these chlorofluorocarbons. As far as we know, it's an industrial gas, and there's a whole class of these. There's many different, chlorofluorocarbons, halofluorocarbons, other compounds. They all have, various absorption in different parts of the infrared spectrum, and they're industrially produced molecules. So if we were to observe something like that, it would be really good evidence of something like extraterrestrial industry.
And I've heard, we covered this a few months ago, that Webb is theoretically capable of detecting these kinds of signals in relatively nearby exoplanets. So it sounds like science fiction, but actually Webb could take a crack at it.
In some best case scenarios, that's right.
You
could potentially use the James Webb Space Telescope for TRAPPIST-1e or some nearby systems like that. Especially if there was elevated CFCs more than we had on Earth. And then you could think about, why would they do that? But maybe they're terraforming the planet, or maybe they don't care, they're robots or something like that. But it's at least an interesting example to show that it's detectable. So I'm not holding my breath to find 100 times the amount of CFCs on TRAPPIST-1e.
Right.
But yeah, we could do the search, and in some ways looking for, you can do the search for free. If you're looking at the planet, you want to know what's in its atmosphere, you don't have to do a special search for CFCs. You're just doing a search to for its spectra to figure out what's in the planet's atmosphere. And so
but it's a duration thing, right? Like you'll want to be scanning for a certain amount of time, so you've got to be able to get time on the telescope.
That's right. And in some cases, looking for a technosignature like CFCs would require less time than a biosignature like oxygen in some cases. So
or like phosphine, if somebody's crazy enough to go searching for that. Yeah. Exactly. So that's a good one. And I guess you can imagine all the industrial processes that we've gone through, and maybe predict ones that might happen in the future?
That's right. So another example is combustion, which we're really good at right now. Combustion produces CO2, of course, which is what we're mainly concerned about. But through a byproduct of combustion is NO2, nitrogen dioxide. And this is just because our atmosphere is full of nitrogen. And so during this high temperature combustion reaction, you get some oxygen combining with nitrogen. And so I think it's about half of the nitrogen dioxide on Earth is anthropogenic. It's associated with our cars, with our farm vehicles, with other uses of fossil fuel to provide energy for us. Now, the supply of fossil fuels is finite. This is a problem we're dealing with now. Even if we have a few hundred or even 1,000 years longer, that's really short on astronomical timescales. So it's worth asking whether we would expect to see evidence of extraterrestrial combustion, because it's not clear if you could really sustain combustion sort of for those long geologic time periods. But it's still worth thinking about.
Yeah.
Maybe you can. Maybe you get lucky and you find civilization right when it's doing that. Maybe have other ways of sustaining low levels of combustion. So that's a technosignature that also kind of, there's some nitrogen dioxide that could be a biosignature. So it's not quite as clear cut as maybe finding chlorofluorocarbons.
But it's almost like you're going to be looking for collections of molecules.
Exactly. And that actually it feeds into my next example, which is agriculture. We just published a paper recently about on Earth, agriculture is a technology because planting things in the ground is not technology. I consider that biology. But with technology about it is the management of the nitrogen cycle. So what you're doing with agriculture is you're actually at first you're taking manure from animals and you're concentrating it and using it to intentionally enrich the soil, which you're really enhancing the planet's nitrogen cycle, even if ancient people didn't know they were doing this. Later on, you start crop rotation, and what you're doing is you're planting nitrogen fixers in alternate years and letting crops go, fields go fallow in alternate years to replenish the nitrogen kind of naturally. But the big invention was, around World War II, when the Haber-Bosch process, which is World War I, Haber-Bosch process was discovered, which allowed the synthesis of ammonia from nitrogen gas and hydrogen gas. And so this is an industrial process. It occurs over a metal catalyst, but it allowed sort of the tide to turn in the war to some extent because you could provide enough. It seems weird, ammonia, but ammonia is a key ingredient for fertilizer. And people who live in farmlands see big bags of this stuff, ammonium nitrate and other products. But so you can enrich your fields with ammonia through this industrial process in ammonia and nitrates, and that provides a source of fertilizer for your crops. Now, this connects to technosignatures because when you apply fertilizer to field, it's a pretty inefficient process. You kind of have to saturate the whole field with your fertilizer, and you get really inefficient uptake by the roots for like a small amount of that. So a lot of this, the nitrogen, the ammonia, and N2O, nitrous oxide, are two products that then are emitted from farmlands in large quantities and reach the atmosphere. And we can see this in satellite imagery for the Earth. We can measure ammonia and we can measure nitrous oxide over areas that generally correspond to high areas of agricultural productivity. So you could imagine a planet that has as much or even more agriculture than Earth as an exoplanet. And if you were to see that, you would have to have the conditions necessary for plants already. So you'd have to have oxygen and water and CO2. But on top of that, if you saw a lot of ammonia and a lot of nitrous oxide, that would be a really good technosignature for agriculture. And that's something you could do for a really long time.
One of the Empire's farm planets.
That's right. Maybe, and exactly. Maybe it's not a planet where there's lots of people living. Maybe it's a service world, and you're using it just for farming and shipping the food off world.
But even so, with the chlorofluorocarbons, say we only had those present in our atmosphere for say 50 years, and then they're going to start decreasing. While the presence of agriculture, that gives you a 10,000 year time scale to some extent. Obviously more obvious.
Maybe longer.
Maybe longer.
Longer. If you're not growing, our problems now are increasing population and increasing energy consumption. But if you solve those problems and you stabilize your growth, there's no reason you couldn't farm, even using the Haber-Bosch process. There's no reason you couldn't farm indefinitely, until the sun expands.
Right. So you've got a stable civilization that is farming to a certain extent, and it's almost like it feels like it's kind of inevitable. Like either they're going to wipe themselves out or they'll figure out how to live in a certain level of stability for long periods of time. And, And if they're out there, then they're out there. That's really interesting. Yeah. What are some other cool ideas that your team thought of?
Well, Thomas Beattie is an astronomer who has this really great idea about looking for city lights. And, there's been some other people who've suggested this, but he did some calculations to show that the LUVOIR mission design, which is now represented in this large ultraviolet optical telescope that's been recommended by the Astro 2020 Decadal Survey. So a mission like that, which is something we're considering doing and hopefully will, could identify city lights, specifically sodium lamps. You see these big orange lamps in cities,
Right.
and it puts out a really unique spectral signature. If you were looking at it, it would stand out quite drastically above other sources of light. Even if you have some sunlight contamination or other things, it would be reasonably easy to pick out with some of these missions.
Now, a lot of the ideas that have been suggested are things that humanity has gone through. And that makes sense because we have some experience. We say, like, we make farms. What if somebody else was making farms? Are there ideas about things that maybe we haven't done or can't do or maybe won't do for dozens, thousands of years?
Absolutely. The idea of megastructures is a whole class of technosignatures that's also really popular in science fiction. And so this is the idea, could you build large structures in space that maybe have sizes comparable to moons or planets? The really classic one is a Dyson sphere or a Dyson swarm. The idea is, you could put a whole series of small free-floating spacecraft all around the sun, say at Earth's orbit or whatever orbit or orbital distance you wanted to, just have a big sphere all around the sun, and you're essentially maximizing the energy you could collect from the sun. Dyson envisioned this as a way to increase habitable living space too. So if population keeps growing, of course, you can have little apartment buildings that are floating around in orbit that you can live on. And then there's lots of designs for things like that you could do to essentially harness the full energy output of the sun. So this is a thing you can think about in terms of how far can a civilization grow.
Right.
Earth is just orbits the sun. We get a little fraction of the sunlight falling on our planet compared to how much energy the sun is putting out. But if you cover the whole sun in all directions, then you're taking advantage of the most amount of energy you could get from our star.
Now, I'll put a link to the actual paper because there are more than a dozen ideas in there. Nuclear war, all kinds of things. But what capabilities do we have today which are well equipped to be able to search for these technosignatures?
Well, I think we're just getting to the point where we're going to be able to look for some of the more interesting ones. I mean, the James Webb Space Telescope will be able to do some. It's not going to be able to do a comprehensive job of looking for technosignatures or even biosignatures for that matter around a lot of planets. It's going to get us a few, which is going to be really exciting because we haven't had any data before. There's some ground-based facilities that are showing promise in their ability to resolve spectra of exoplanets. We're not really able to do that yet with Earth-sized planets, but we'll get there. We'll eventually be able to with some of these larger larger diameter ground-based telescopes. Trying to think of what there's probably a lot of work that can still be done in archival data. Like, we have missions like the Kepler mission, which is kind of, had its run and then had a second leg. There were some exciting discoveries from, potential technosignatures like Voyager star, which, people still talk about what is this exactly? Are there other events like this? Is this, a decaying comet swarm or something like that? Probably not a megastructure, but that was exciting. And it was the kind of anomaly that we hope to find. And we want to find anomalous things like that in the search for technosignatures. So there's still probably work to be done to look at existing data sets from things like the Kepler Space Telescope to look for other anomalies. The TESS mission is essentially doing something similar to what Kepler did, but for nearby star systems. So I haven't seen anything anomalous yet come out from TESS, but there's a potential that we could detect something weird that's transiting from the TESS mission.
Right, like for example, like TESS is designed to watch for that dip as a planet is passing in front of the star. But what if the dip had a weird shape, like it was a triangle? That was the object that was moving in front of the star. It would actually give a fairly detectable signal that's different from a planet.
Exactly. Yeah. If you had some artificial object orbiting, or you had a star shade, or any any number of things you could imagine. You could potentially see something like that with tests.
That's really interesting. So now you mentioned, as we sort of got into the interview, that half of your time, or some of the time, was spent thinking about what is currently possible, and then you said that you then set your imaginations loose to figure out what would be ideal. So what would be some perfect technosignature hunting missions that you could envision?
Well, one of the things that we're missing now, even with some of the missions that are being planned, is to be able to look at exoplanets in the infrared. And I mentioned that would be important for something like chlorofluorocarbons. Now, the James Webb Space Telescope can do this a little bit for some, nearby star systems, right. Mostly M dwarfs. What we really need to be able to do is to do this for a wider range of stars, including stars like our sun. To be able to look across the full spectrum to get sort of a statistically meaningful sense of what planets have what types of spectral signatures. So a lot of these industrial compounds, these industrial technosignatures are going to have an infrared, mid-infrared absorption signature. The only mission that's really kind of thinking about doing that right now is the Large Interferometer for Exoplanets, the LIFE mission, and it's kind of under study by ESA right now, the European Space Agency. It's not clear if that's going to be selected or not.
I haven't even heard of this mission, which is weird because I've heard of them all. So hold on,
it's just a mission under study. I mean, this is good that we're promoting it because that's partly what they need. Is I think in order to move on to the next level. They need support from the community.
Yeah.
So it's just a mission being designed for ESA's next selection of flagship missions.
And the life interferometry.
The Large Interferometer for Exoplanets.
Okay.
It's the acronym LIFE.
LIFE.
But see, if you Google LIFE, it's really hard to find.
Yeah, no. But I'm sort of envisioning what it would be. Would it be a ground-based or a space-based interferometer?
That would be a space-based interferometer.
Wow. So like sort of like the terrestrial planet finder, but not canceled.
Exactly. Yeah. I mean, so when I was in grad school, or when I was applying to grad school, I was promised the terrestrial planet finder was going to launch in 2017, and there was going to be two of them. There was the interferometer and also coronagraph. But then ESA at the same time was planning the Darwin mission.
Yep.
So in some ways, this LIFE mission is the successor of the Darwin mission.
That's really interesting. It is interesting. I mean, this is a total rabbit hole, but that ESA is really taking up a lot of the interesting exoplanet hunting missions. You got the Cheops mission. You've got the Ariel, which is coming in 29. They've got a lot of really, Darwin, as Plato, you mentioned, Plato. Yeah, they've got a lot of really interesting missions for this kind of work. They've really taken on the mantle, and not to mention what Gaia can do just in terms of hunting planets. There seems like a very focused effort in uncovering planets coming out of ESA. It's great to see it.
Absolutely.
So, but you're looking at some of this still sounds like existing missions. So let's imagine, I guess the problem is, like, if you made a technosignature hunting spacecraft, it would also be great for all kinds of things. Like, it would be a gigantic telescope with a star shade or whatever, and the regular exoplanet astronomers would love to use that too. Are there any kinds of missions? I mean, I'm thinking about things like surveys for Dyson swarms or surveys for type 3 civilizations. Are there any kinds of missions that would give you a very unambiguous signal but maybe wouldn't fall under the purview of an existing mission?
Well, you could certainly do a better job at that. So for what you're saying, like looking for these Kardashev type 2 or type 3 civilizations that have settled many star systems, you could certainly do a better job at that. And then this would again be looking at infrared, looking for waste heat. But it'd be similar to like the WISE mission or something like that, or Spitzer, like a follow-up. But again, that would have really useful general astrophysics properties again.
Find all the brown dwarfs and rogue planets, and yeah.
No, I think that the specific ones that are really technosignature unique would be within the solar system, and there would still be other science that you could do. But I think if you were to say we want to look at Lagrange points to see if any artifacts have collected there, or we want to look at the surface of the moon to see. So when my colleague Daniel Egerhausen is doing this, actually, he's looking at high resolution images captured by the Lunar Reconnaissance Observer, the moon, and using untrained machine learning algorithms to look for anomalies to see if you can find any technology on the moon. Now, we know there's technology on the moon. There's the Apollo landing sites. The Russians have crashed into it a few times and landed there. So I don't think he's finished yet, but that's at least there's some ground truthing you can do to make sure you can find that.
Interesting. So in theory, you would do this machine learning algorithm would just stare at all the LRO data, and hopefully it will find the Apollo landers and go, these are weird. We don't have a natural explanation for what these things are, but then also there's this weird alien robot von Neumann probe factory over here on the, on the far side of the moon, for example. That would yeah, that's really interesting. So let's talk about this some more then. What are some other places we could look inside the solar system for some kind of evidence? Because, in my opinion, this idea of von Neumann probes, where are all the aliens? The classic Fermi paradox. You would think that there would be some evidence of some extraterrestrial civilization having come through the solar system, used us as a supply depot, and then moved on as they continue their exploration of the Milky Way. Where would be the best places to look for this?
Right. Well, that's the Fermi paradox.
Yeah.
I mean, so there's the surfaces of planets, right? There's, the moon and Mars are nice places to look because the surfaces aren't resurfaced very often. And so if something were to land there or to crash there, it'd be easier to see. Something landed on Earth, it might be a lot harder to see. There's oceans it could fall in. Maybe if you're lucky, it falls on like a part of Antarctica where it doesn't snow very often and you can find it. Otherwise, we have weathering on Earth. There's lots of processes that destroy and hide things. The gas giants are difficult because they don't really have a surface, and so something flies into it, it probably gets destroyed. But maybe they're moons, so anything with a solid surface. But the asteroid belt, if you're talking about von Neumann probes or any kind of alien ship passing by because they need resources, look for evidence of asteroid mining. Maybe they came through and picked up some water and some iridium and moved on.
And it is interesting because it could have happened at any point in the solar system's 4.5 billion years. An asteroid that was heavily mined out would be obvious and would be largely unchanged for billions of years. So it would be a very unambiguous signal that somebody came by, and maybe there would even be leftover parts of their hardware.
Unless they took the whole asteroid, then we never know.
Right. Yeah. Turned it into a spacecraft and then flew off with it. And you mentioned that you didn't talk about SETI as part of this paper, but how do you feel that SETI fits into this larger work as well?
It's all part of it. Technosignatures is just any way of looking for life. And so I still will say SETI. I like talking about technosignatures because it focuses on detecting evidence of technology. You don't have to talk about what is intelligence. That's the kind of a rabbit hole to get into. And you, of course, there's intelligence on Earth that might not give off astronomically detectable signals. And so just focusing technology, but it's the same thing fundamentally. And there's a lot of great work going on in radio right now. Breakthrough Listen is really, kind of one of the leaders in this right now. I think they're a little over halfway through a 10-year project to do a whole sky survey. Now, they're still not doing what you really should do, which would be expensive, which would be to look at all directions of the sky at all times, at all frequencies. They're looking at, a lot of stars for a few seconds. But what if you look at a star for a few seconds and then they transmit a couple minutes after you were looking at them? You don't know. They're testing a hypothesis that there's a beacon that's always on around some of these stars, and it's a fine experiment to do. But I think they would agree that what you'd really want to do to really test the SETI hypothesis, you have to steer everywhere all the time, all frequencies, probably for a while.
Yeah.
But
How
again, that would have useful applications for other parts of
right, of course.
astrophysics.
That's how
And
you
yeah,
sell your astroseismology survey is that you are, you're staring at all of the stars all the time.
so
And
I
so
think what you're getting at. We can keep talking about all the details of it, but in general, there's not many, if very few, if any, missions that would do just technosignature science and nothing else. But I think what you could do is right now you have missions that are for general astrophysics, and we got lucky with this astrodecadal where it's for biosignatures too, which is really exciting. Um, you don't really have any designs being optimized for technosignatures at all. And what I think is great now is that these people are starting to consider, like other scientists, starting to take technosignature science more seriously. I would love to see in this next generation of missions for technosignatures to be explicitly called out as one of the science objectives in the mission, even if it doesn't cost them anything else. That would be a huge step.
yeah,
So a mission that does not exist is the kind that adds money behind technosignatures, even if it's not 100% for technosignatures, but where
right.
technosignature science is actually a driver of the design instead of just something you get for free, if
And
that
when
makes
you
sense.
say money, and this is sort of going to lead into the next set of questions that I had for you. It's like when you look at, say, the Parker Solar Probe, and they list their priorities to understand the solar atmosphere and understand the interactions of and the solar wind and so on and so forth. They have a list of priorities. And I guess that means that if you're going to try to answer one of those questions, you can get funding for your research and be able to get access to the instrument and et cetera. And in many cases, if you come to say, I want to use James Webb to scan this star system because I think there might be a Dyson swarm there, they'll look at the list of priorities and go, we don't see that here. So do you think that there is this shifting towards an acceptance, an interest in searching for? I mean, even just like even astrobiology has finally been allowed to show up at the table. Do you think we're at the point now where there can be this as set as a priority?
Oh yeah, I think absolutely. I think what you said could be reasonable. I think if somebody were to have a compelling observing proposal for the James Webb Space Telescope to look for a Dyson sphere, you would probably have some astronomers on the review committee that would give it a funny look. But you might get some that would say like, well, let's just take this seriously as scientists and see if they make a good case or not.
Right.
So that's part of what we're trying to do is just get scientists to get over the giggle factor and just look at it for what it is. Not all technosignature ideas are good, but just evaluate it like you would any other idea in science. So I think we're moving toward that, where if the telescope can do it, and it doesn't, it's not, they don't have to build anything extra into the telescope to look for technosignatures. Then essentially it's free science for them. Um, but if
Right.
you're like a future mission that what would be really great, and this is wishful thinking, like that second paper mentioned, to have missions where technosignature science was really driving the design, and you're
Yes.
still doing other things, but you're saying like, well, we really want to see CFC, so we're going to make this telescope measure way out into the infrared, and the science justification is because we want to see industrial molecules. And there's other things we can do with it. Right now, it's backwards. It's the other way. It's like if you're lucky, you can fit technosignatures into what they're already doing. Um, but
It. What
yeah,
about like a specific target? A.V. Scott and Flowers mentioning in the chat, like if I was in charge of James Webb, the first thing I'd image would be Proxima Centauri. Um, would there be a mission? Like, is there a specific target that you think might be interesting enough, maybe because it's close, that it's worth analyzing as long as you can, as opposed to a more general survey or something that can be turned at lots of different targets?
oh yeah, I think that's probably what will happen with JWST. I think TRAPPIST-1e will certainly be surveyed. Um, I don't know about Proxima, what its capabilities are for that, because but
Right.
Um, the James Webb Space Telescope is not going to get a broad survey of lots of exoplanets in terms of like detailed spectra. We'll probably get detailed spectra of one or two planets.
But like you know of the solar gravitational lens idea, where you fly a mission out to 500 plus astronomical units and you use the sun, the gravity of the sun, as a lens. And the trick with this is that you have this tiny little cylinder that you have to fly your spacecraft down, and you can only observe one planet, and that's it. But you get to see the planet at megapixel resolution, which would be great to see an exoplanet at megapixel resolution. Do you think we're at the point where we have enough interest? Do we have interesting places that would be worth spending a lot of time studying?
Not yet. No, the most interesting planets are still to come. Yeah, what we have now is exciting because we know that there's planets everywhere, and we don't have any reason to doubt our ability to find a habitable Earth planet. There's planets everywhere. We just have to keep looking. But we've found the planets that are easier to find, which is not necessarily the ones that are the most interesting for searching for life and technology. So yeah, if we were to build something like that, I would say we've got to wait. We don't have the best target yet.
And like but across the spectrum, then you mentioned Tabby Star. I know SETI researchers like the WOW signal. There's a few others that are interesting. Obviously, you can't go back in time and study the WOW signal better. People have tried, but like are there any interesting anomalies that would be worth investigating more deeply at this point? Or do you think we haven't discovered enough weird stuff yet?
As far as exoplanets go,
or just anything really, like be it inside the solar system, outside the solar system, anything.
Things. Yeah, I don't know that there's anomalies that I can think of, right off the top of my head that are, there are other things like Tabby Star. I don't think they're necessarily. I think it's probably not a Dyson sphere or something like that, just based on how the discussion is going. But there's probably more to be understood with those. So in that sense, yes, we should keep studying that. No, I think we need to keep looking for anomalies. I think that was an interesting one because it was an unexpected anomaly. Often when you find these anomalies, they get explained after you put a little bit of effort into it. But you weren't expecting it. So, an example is the very first discovery, the first class of exoplanets that was discovered were hot Jupiters.
Yeah.
They were large, massive super Jupiter planets, very, very close in to the star, almost like a binary star. These were not really predicted by the planet formation astronomers at the time. But they were really easy to see because it had a huge gravitational tug on the star, the planet did. And so these were found everywhere. And so then there was a bunch of astronomers studying hot Jupiter. So that was anomalous. And then it was resolved relatively quickly afterward. So I think there's things like that. We just need to keep looking for anomalies to see what might be out there.
Yeah, it does feel like trying to examine places is premature right now. Like, now is the time for the Vera Rubin observatories, the Gaia missions, the Nancy Grace Roman missions, the ones that are going to give us these giant surveys and start to at least make note of the anomalies, and then you can make those follow-up observations. Ariel's another example, and then you have, I'm trying to think, like, I think about, like, say, Cheops as a exoplanet characterization mission. It can't find planets, but it can study the ones that have already been found and give us more information. And it's all so new that we don't even know the weird stuff. We don't have a list of the weird stuff to look at yet.
Yeah, that's right. And, we don't, there's a lot of unexplored territory within our own solar system. And I think that there's looking for interstellar objects, there's looking at planetary surfaces, there's looking at these gravitationally stable points between, within planetary orbits, these Lagrange points where debris can collect in a stable gravitational configuration. That's very unexplored still. I don't know that there's any anomalies that we found. There's one anomaly I can mention that has been published, but other than that, I think we just need more that needs to be searched, surveyed.
Yeah.
The anomaly I'll mention, there's a paper by Beatrice, I forget, I'm going to mispronounce her name, Villanova. She looks at, she has this project called the Vanishing Star Observing Project, and she looks at old photographic plates from the pre-satellite era, and then compares them to observations of the same patch in the sky today. And so if there's any differences, if there's any points of light that existed back then versus now, you found something transient. So you found an object, whether it was a comet or something that was not a star.
Yeah.
Or something that went supernova or whatever, the star vanished for whatever reason. And so she did publish this paper recently where there was, a series of anomalous, observations that appeared in this old photographic plate, does not occur in modern observations. And she's ruled out all the other conventional explanations that she used to explain the other things that she's found. So she ruled out things like comets. There were no satellites in the air at that time. So we don't know what it is, but that's an anomaly that's been published, and it's quite interesting. And, whatever that would be, it would be within the solar system, relatively close to Earth, not like the distance of Jupiter or anything like that.
Yeah, that's really
so there's things like that, we just need to keep looking for anomalies to see what might be out there, and then try to piece some of this stuff together.
That historical, like the longer we can observe, and as long as that information is kept in good archives and is searchable, then you start to get access to that time period as well. So you can start to detect evolutions over time of things changing. Maybe something that wouldn't be obvious today, if you looked at it over the course of, say, 100 years, maybe something would be obvious. And that's really exciting too. But I do like that idea of scanning the skies before there were satellites to search for satellites.
Yeah, and Starlink's going to make that even harder now.
Yeah,
but
yeah. What is your instinct for the Fermi paradox? What do you think explains the Fermi paradox?
Well, there's sort of two ways that I go with this. One is, I've published a couple papers, one called The Sustainability Solution to the Fermi Paradox, and then another one with Brendan Mullen more recently that's looking at very similar things. Look at our growth rates, our population, but then also energy consumption. And, this is not something that's sustainable for a long time scale. We talked about this a little bit earlier, but you could do something like farming in a sustainable way if you can control that growth. So the Fermi paradox is kind of predicated on this form of exponential growth. The way that the question often asked is the planet sends out spaceships to settle other planets, and they send out too, and you very quickly settle the whole galaxy. And so once you do that, you either have to immediately stop growing, or else you exceed your carrying capacity and you collapse. And so that's one way I look at this, is if exponential growth is something that happens, it's probably unsustainable. And so maybe one answer to the Fermi paradox is it did happen. There was massive galactic attempted, and either they collapsed before they got there, or they got there and then collapsed because they didn't figure out how to put the brakes on.
Right.
And so then maybe who's left is the slower growing civilizations that maybe they grow, maybe you can go from one star system to another, maybe not, but you grow within your carrying capacity. And so, yeah, I kind of think whoever's around has to grow within your carrying capacity. It might be that you can only grow to the bounds of your stellar system, and that interstellar travel is really hard and it's just sort of a novelty for exploration. Maybe you can grow, to multiple star systems, but there might be a civilization in some cluster of the galaxy and they haven't reached the whole thing.
Right.
Now, the other answer that I like, though, is that we're ants and we have no idea who's out there. Did I pass an ant hill? Do they know that I walk by? Do they know the kind of technology that's going by them?
Yeah, I've been bit by an ant. So ants are definitely aware that I'm here.
But do they know what kind of technology you're carrying? Do they know about your wristwatch?
I don't think they care. Yeah, I don't think they care. They need to bite. So,
yeah.
I think, like, I wonder about that idea, and I know what you mean, but it's almost like at a certain point, if we can't perceive them, then they're as if they don't exist. Functionally.
That's right. And so the question is, what we can never fully rule that out. All we can do is try to expand our minds to think more broadly about what could be observable. But if there's nothing observable, then we can't do a scientific search for them.
Yeah, yeah.
But it could be that we just don't know how to look for it. We could be looking right at it,
yeah.
and we just don't know what we're looking for.
There was a really interesting idea in the Three Body Problem series. I don't know if you've read them by.
I'm familiar with it. Haven't read it
it's usually the gist is, and I don't want to spoil it, but part of it is like humanity is detectable by our impact on the environment of planet Earth through the cities and through the environment and through pollution and all these kinds of things, the changes that we've made, the shapes of the cities, etc. And what if life's impact on the universe itself, like the actual fabric and structure of the universe itself? What if the universe that we find ourselves in is not what the natural universe looked like? That in fact we are the result of technologically advanced civilizations depleting the universe as a resource. And it's a very sort of fascinating idea that we think when we look out into the universe, that we see stars and planets and galaxies and stuff, that is what naturally formed, in the same way that we look around the Earth and we see rocks and oceans and forests, etc., and we think that is the natural environment. But when you hop into a city, you see a different environment. And what if the universe that we find ourselves in today is the equivalent of a city? That we just
the whole thing is engineered.
Absolutely. Yeah, we can't perceive it. We just can't perceive what it is and what the impact is and what pristine universe would look like, because we're already, things have been the good stuff has already been taken out of the universe, and it's a really interesting idea. So what's the best place for people to follow your research?
Best place to follow my research? I mean, you can follow me on Twitter. I don't post about politics. I actually don't like Twitter for that reason. So all I do is post about my research.
Perfect. Yeah.
I have a webpage, Haqq-Misra.net. You can follow Blue Marble Space if you go to bmsis.org. I think if you click on About, or maybe on the left panel, you can join our mailing list, and you'll get updates, for my work and then my colleagues, all the kinds of stuff we do. We send a newsletter once a month.
Fantastic. Well, Jacob, it's been a pleasure to talk to you, and good luck. If you do find that technosignature, please let me know.
You'll be the first one I call.
All right. Awesome. All right. Take care.
Thanks a lot.